Hi, I'm Dustin. I'm a developer advocate at Google. I'm also the organizer for the PyTexas conference, will be in Austin, Texas, October 24th and 25th this year, if you want to come. I also work on a bunch of Python things, including Python package index. But I'm not here to talk to you about any of that today. Instead, I'm here to talk to you about static typing, and I want to start with a pop quiz. So, is Python dynamically or statically typed? So maybe you think, yeah, Python is a dynamically typed language, so it's dynamically typed. Or maybe you think, this is a talk about static typing in Python, it's probably statically typed. Or maybe you think this is actually a trick question. And it is. This is a trick question. So the answer is that Python can be dynamically typed, but can optionally be as statically typed as you want it to be. And that answer might not make sense to you. And if it doesn't, that's okay. You're watching the right talk. The steps to understand the answer to that question are: first, we need to talk about types in Python, then type systems in general, dynamic typing in Python, static typing in Python, and then once we understand that, we can talk about how to use static typing, when you should use static typing, and also maybe when you shouldn't use static typing. So let's talk about types, and let's specifically talk about the type built in Python. So in Python, if I type of 42, I get a response class int. I can do type of 42.0, I'll get a class float. Type of foo is class string, and type of foo and bar is a class list. And you might say, oh, I recognize these. These are built-ins that I can use to change one type into another type. And you'd be right? We could set a variable a equals 42, and we can change it into a float by calling float on it, and cast it to a string, and then we can cast it to a really ugly list. So maybe you've had a weird bug where a string actually got turned into a list that looks like this. Guess what? That is a type error. You are in the right place. It would seem like these are just the only types available to us, right? Int, float, string. But these are actually just classes that have corresponding built-ins in Python. So basically we're doing class matching here. When we do something like is instance 42 int, we're seeing if 42 is an instance of the int class. Int is just a built-in here. There are other type classes too that don't correspond directly to built-ins, like, for example, none-type. I'm sure we've gotten that a lot in our Python code, right? None-type is the type of none, but we don't use none-type to describe it. Similarly, there's a function type, but we don't use function to define a function. We say def, func, etc., etc. There's also lots of other ones, like the ellipsis type, and these all don't correspond directly to built-ins. The place we get them from is if we import types, we can get this giant list of all the types that are available to us. Many of them live in the types module, and all of these can actually be used to instantiate a new type. So for example, a function, we could instantiate a new function with the function type, open close parens with some arguments in there. But we don't really do that, and it's for a good reason. It would end up looking really messy. Instead, we'll do it the normal way with def function name. So when we say that Python is a dynamically typed language, it means a few things. It means, first of all, that variables can be any type, and that the type of a variable can change over the course of the runtime of your program. So for example here, I can import random and set a equal to the value of random.choice that contains a list of three things: the integer 42, the float 42, and the string 42. Now if I call type a on the result of that variable, what type is a? And the answer is that we don't know. This is non-deterministic. It could be a string, it could be an integer, or it could be a float. It depends on what random.choice decided to choose. Dynamic typing also means that the arguments and the return types of a function can be any type as well. In Python, if we write a function like this, frobnicate of abc, and returns a plus b plus c. If we write a function like this, how do we know that we're getting the types that we're expecting? So if you saw this function and you didn't know what it does, what would you expect the argument and return types to be? So you might guess that they're integers, and that would work, right? We could call frobnicate with 1, 2, and 3, and it would return the result of the sum of those three numbers. But so would strings and lists, and basically anything else that supports the addition operator here too, right? We could pass it three strings, and it would eventually just concatenate all of these three strings together and return that value. What we can't do here is mix integers and strings together. So we can't pass 1, 2 as integers and foo as a string, because that's a type error. We can't use the plus operator to combine integers and strings. All right, so that function is confusing. How could we possibly fix it? One thing we could do is this. We could write really long and detailed doc strings to describe what the parameters and the return type of the function are. So if you do this, I would ask yourself, is your company paying you enough to do this? Because this is a lot of work. And at the end of the day, this doesn't actually even have any control over the runtime of our program, right? This is just documentation. It doesn't ensure that our developers are actually calling this function with the correct parameters that you described in the doc string. Another thing we could do is we could assert on the argument types and the return type of everything that's passed to our function. So for each of the parameters, we assert that the type is the type that we're expecting. We do our business logic, and then we assert on the return type and then return it. So we don't do this either. And actually I gave this talk once before and I said, nobody does this at all. And someone in the audience says, well, yeah, actually we do this. And so while this is valid, right, this is type checking, there's some problems with it. First of all, there's a little bit of overhead here. Every assertion that we have to do here slows down our program just a little bit. And you can optimize that out at runtime, but it's not that common. The other problem here is that what if you forget to write an assertion, right? Then your program is missing some type checking. So we don't do this. What do we do instead? Instead, what we do is called duck typing. Duck typing means that if it walks like a duck and it quacks like a duck, it is probably a duck. So this means that we determine the types of a function or a variable based on how it's used. In each of these, you can kind of guess what foo and bar are based on what's being done with it. So in the first example, bar is some kind of iterable. It might be a list or a string or possibly even a dict. And foo is a list comprehension, so that's going to come out in being a list. In the second example, bar is being compared to 0, so it's probably something like an int or a float. And in the last example, it's a little bit ambiguous actually, right? Is bar a function or a class? Like what is foo going to be here? It actually could end up being anything. So now let's talk about static typing. Static typing meaning as in a variable type is defined and it's not going to change. And there are actually lots of statically typed languages. Here's some examples of the same function we were just looking at in those languages. So here is an example of from in C. Here it is in Java. It's a dead giveaway with a public static int blah 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 blah. This one is Rust. You can sort of tell it's Rust because Rust has really fine-grained control of the integer types. The U8 here is an unsigned 8-bit integer. And this last one is TypeScript. JavaScript itself doesn't have types, but TypeScript is an implementation of typed JavaScript. And this is a dead giveaway that it's TypeScript or JavaScript because in JavaScript, everything is all numbers are just the same type. They are a number. So we can kind of put languages into two categories. First, dynamically typed languages and statically typed languages. And we got to put a little asterisk here next to Python because that's the content of this talk. And technically Ruby is going to get optional static type checking when Ruby 3 comes out later this year, but I'm going to leave it off the list for now. So earlier I said Python is dynamically typed, but can optionally be as statically typed as you want it to be. Now, the thing to note here is that this wasn't always true. And the story of static typing in Python is also kind of the story of static typing at Dropbox. Dropbox is a company with millions and millions of lines of Python code. And basically at some point in their history, they decided that having that much untyped Python code was actually a liability, right? It was slowing down their developers and making things harder for them to create new features and do actual development. But there were some other things that led up to it as well, and I'll talk about those here. The first was PEP 3107, function annotations. We got this in 2006 with Python 3. And this let us write a function like this and add some extra metadata to annotate the arguments and the return value of the function. So the thing to note here is that this has zero effect on the execution of the function, and we can put whatever we want in as these annotations. All of this gives us is an attribute on the function called dunder annotations that gives us the result of evaluating all of these annotations. So here A would be X, B would be the sum of 5 and 6 and 11, C would be the empty list, and the return type would be 9. So anything compiling this function or interpreting this function has access to these annotations, but they're not. This isn't maybe super useful. And the PEP itself sort of listed a whole lot of uses for this annotation thing. They basically all boil down to we could do something that looks like static typing with this. And also maybe we could stick some documentation, but basically the purpose was let's do something that looks like static typing. So if we think about this through the lens of static typing, we could write annotations like this, where the annotation itself is the type of the argument that we were expecting and the type of the return type. But still, this doesn't give us any way to actually evaluate whether this function is being used correctly elsewhere. It's still just metadata. It also doesn't give us a way to annotate variables. We can only annotate functions, their arguments, and return types. So around the same time as this PEP was authored, Yuko Taslo, a PhD candidate at University of Cambridge, was doing his PhD research, and his research was on the unification of statically typed and dynamically typed languages. Sounds pretty interesting. He wanted to use the same language for everything from a very tiny script to a sprawling multi-line codebase. And his research was also focused on the gradual growth from an untyped prototype to a statically typed product, meaning you don't have to do it all at once. You could start with some small parts of your codebase statically typed and slowly grow and add static typing to the rest of your codebase. Sounds pretty cool. So he published his research in 2011, and his thesis was basically this. Adding a static type system to a dynamically typed language can be an invasive change that would require coordinated modification of the existing programs, virtual machines, and development tools. However, optional pluggable type systems do not affect the runtime semantics of programs, and thus they can be added to a language without affecting existing code and tools. This sounds really great. So at PyCon US in 2013, Yuka introduced Myapi. And if you've heard of Myapi before, this is probably not what you're thinking of. In his abstract, Yuka describes Myapi as an experimental variant of Python that supports writing programs that seamlessly mix dynamic and static typing. This is not really true when we talk about Myapi today. In his research, he wasn't able to use an existing language to determine how to do this. He couldn't use Python the way it was. So instead, what he did was he created his own language instead, which isn't really that crazy for theoretical research. And this is what the variant looked like. It could be compiled to Python, and it kind of actually looked a little like Python if you squint at it. The issue is, even with function annotations, which existed in Python at the time, Python couldn't support everything that was necessary to be completely statically typed itself. Yuka said he eventually presented his project at PyCon, and afterwards, he talked to Guido van Rossum about it, the BDFL of Python. And Guido convinced him to drop the custom syntax and just stick to straight Python 3. Let's just do this in Python 3. So Myapi also included a static type checker for this Python variant, which was modified to check Python instead, and that's what we actually think of as Myapi today. The next thing that happened in 2014 was we got PEP 483, which is the theory of type hints. And this was Guido putting down some ideas about how static typing should work in Python. One thing this PEP describes is optional typing, which means that adding annotations shouldn't affect the runtime of your program. An annotated function should run the same as an unannotated function. And I think this sort of comes from some lessons we learned from the Python 2 to 3 migration. Basically, adding static typing shouldn't get in the way of your program. Another thing it describes is gradual typing. Basically the idea of let's not try to do this all at once. Gradual typing allows one to annotate only a part of a program and thus leverage the desirable aspects of both dynamic and static typing at the same time. In addition, it describes a way to do variable annotations, building on PEP 3107 to give us a way to annotate more than just functions. So this means that with our original function, we could add a type annotation to the actual BizBaz variable here. It introduced type hinting for Python 2, because function annotations didn't exist before Python 3, but even those stuck in the past kind of deserve static typing. So in Python 3, we could write a nice little function like this, where all the argument types, return type are annotated. But in Python 2, we have a way to write the same function, same type annotation, but just use type comments instead. Finally, it also introduced some special type constructs. So these are fundamental building blocks that we need to do static typing. And these build on the existing types like int, float, string, none type to give us some new types like any, which is consistent with any type at all, union, which would be the combination of one or more types, optional, which is an alias for the union of a type and the none type, a tuple, which would be a tuple whose items have those types, callable, etc. So this lets us write a function like this, where fromDecate takes first an integer, then an integer, and then the third argument here could be an integer or it could be a float, depends on how the user calls it. The PEP also gives us container types. Container classes are things like lists and dictionaries that contain other objects. So container types are really important because they let us define the types inside of a container class. So for example, I could create a users variable here that is typed as containing only integers. And I can add integers to it and that's fine, but if I try to append something like a string, it will fail. And similarly for a dictionary, I can type the key and the value. So here, examples contains keys of strings, values of integers. So I can set some guy equal to 42 and that's fine, but I can't use a key of an integer. This PEP also gives us generic types for when a class or function behaves in a generic manner. So if I wanted to type a function as taking an iterable, and I don't care if it's a string or a list or basically anything that I can iterate over, I can use the iterable generic here. And finally, we have type aliases, which allow us to be more succinct with our types. So this means that if we wanted to be more like JavaScript, we could create a number type that's a union of all number types available to us, and we can annotate our function with it. The next PEP we get is PEP 484, which is type hints in 2014. And this standardizes everything in PEP 483 and Myapi's behavior. It introduces the typing module to provide standard definitions, fundamental building blocks, and tools. It also introduces a lot of details about edge cases and specific use cases. Essentially, it's how to build a type checker in Python. And it leans really heavily on what Myapi is already doing at this time. In Python 3.5, we got PEP 484 support and the typing module. In 2016, we got PEP 526, syntax for variable annotations. So the existing comment style annotations was great for Python 2, but not great elsewhere. So this lets us take a comment style annotation like this and move it actually into part of the variable declaration. One of the problems with comment style annotations was that we couldn't define a type for a variable and not specify an initial type. So here now with PEP 526, we can just say the captain variable is a string and it has no initial value. And similarly for class variables, we can now do those inline like this. So with Python 3.6, we got PEP 526 support, and we almost had everything to do static type checking in Python, except for a type checker. Now, there are two types of type checkers, static and dynamic. Static type checkers don't actually run your code. They look at it at rest when it's not being evaluated. Dynamic checkers, however, would check types while your application is actually running. So at this point, Myapi had transitioned from being a Python variant to just a type checker, and it was available on PyPI. You could just pip install it. So you could pip install Myapi, you could write some type annotated function, and you would run it, and Myapi would tell you if you were using your types incorrectly. So there are actually a bunch of type checkers besides Myapi. At this point, Myapi is mostly owned by Dropbox, Google has PiType, Facebook has Pyre, Microsoft has Pyrite, PyCharm actually has a type checker built into it, and really most of these can be integrated with your editor, so you can sort of mix and choose as you'd like. There are also others that don't support the PEP 44 spec, and also a bunch of dynamic type checkers that run at runtime. So disclaimer, I work at Google, and the inevitable question that I get here is, if they all support PEP 484, what's the difference between them? Why would I choose one over the other? So I've mostly used Myapi and PiType, so I'll talk about the differences between those two. The differences between Myapi and PiType come down to sort of two areas. One is cross-function inference, and the other is runtime lenience, and I'll talk about these in a little more detail. So this is what I'm talking about with cross-function inference. Here we have a function g, and when we call that function, it's calling another function f. Now, if we try to run this example, we'll get a type error because we're trying to combine a string and an integer. If we run this with Myapi, it doesn't produce an error, and the reason is because Myapi doesn't have the ability to infer types across multiple function calls like this. Whereas if we run this with PiType, we'll get the error that we expect, and we'll see that this is going to produce a runtime error. The other difference, runtime lenience, sort of comes down to a difference in philosophy between these two tools. So PiType is going to allow any operation that will succeed at runtime and doesn't contradict any existing annotations. So here we have a function f that's annotated as returning a list of strings, and in that function we create a list that contains a string, we add an integer to it, which would be sort of like mixing types, but then we do return a list of strings. If we run this, we get the answer that we expect. There's no runtime type error. We get PyCon 2020. If we run this with PiType, it says that there's no errors. This isn't going to produce a type error at runtime. But if we run this with Myapi, it says that we're trying to append an integer to a list that's supposed to have types of strings, and this fails. So you might be saying, why though? When and why should I use static typing? And first I'll say when you shouldn't use static typing. And the answer is basically never. You should use static typing liberally as much as possible. It's never really going to hurt. The one thing I will say is that static typing is not a replacement for unit tests. And there is a bit of an argument here because sometimes when you look at unit tests, they kind of just look like you're just testing the input and output types of your function. But really, unit tests are kind of a bad replacement for a type system. And in reality, you probably actually just need both unit tests and static typing. So when should you use static typing? Basically, as much as possible. You should use static typing when you're millions of lines of scale. So if you're Dropbox, Google, Facebook, you've probably already invested a lot of money in static typing because the lack of static typing, like I said before, is a serious liability for Python at scale. You could have said at Dropbox's scale, which had millions of lines of Python, that dynamic typing in Python made code needlessly hard to understand and started to seriously impact productivity. So I made a little graph for you here. As the lines of code in your code base increase, your desire to add type annotations is also going to increase, but the ease of adding type annotations is going to go down. So you're probably here. This is kind of where you should migrate. This is probably actually where you're going to migrate. So keep that in mind. You should use static typing when your code is confusing. So let's be honest, we've all written confusing code. You can kind of think of annotations as machine-verified documentation. So if you feel the need to document the input and the output of a function that you're writing, it should probably just be statically typed. You should also use static typing when your code is for public consumption. For example, if it's a module on PiType. Adding type annotations helps developers know how to use your APIs and helps IDEs know how to consume your APIs. Also, if your users are already using static typing, they will love you for it. You should use static typing before migrating or doing a big refactor. Basically, add static types to all the mission critical parts of your application, and then go and do your migration refactor and see if any of your type annotations start to fail. That'd be a place where you could probably find some bugs. You can also use static typing to just experiment with static typing. It doesn't hurt. Start with some small dusty corner of your code base, or start with the most mission critical part of your entire application. Add a little bit of static typing, add a static type trigger, and see what happens. So how to use static typing in Python in just 5 easy steps. Step 1, migrate to a Python greater than or equal to 3.6. This is optional. You can do type comments in any version of Python, but you should probably migrate anyways, let's be honest. Step 2, install a type checker locally and integrate it into your editor. I don't care which one, and you can even install more than one if you really wanted to. Step 3, start optionally typing your codebase. Start with your hairiest files or the easiest to type files. Don't try to do it all at once, and remember, it's gradual for a reason. Pick critical areas and then start there. 4, run type checker with your linting and run linting in CI, which you should probably be doing anyways. And 5, convince all your coworkers to join you. If you need help convincing them, you can just show them this talk on YouTube. Thanks for watching. You can follow me on Twitter at @di_codes. I also want to give a huge thank you to the PyCon staff for everything they've dealt with and everything they've done to bring this conference online. They absolutely deserve your thanks as well, so be sure to let them know you appreciate all the hard work that they're doing. See you next year.